So, hello everybody, and welcome to this month's um, issue of the OSNA CPP meetup. And this time we have another guest. Today we will welcome Rober Seacord from Woven at Toyota. He is the standardization lead there and the convener of the IEC C Standards Committee, author of several books, including Effective C and others. And today we have him here with a talk about dangerous optimizations. So, as it is like our tradition for the OSNA CPP meetup, we are doing this with a live stream first and then a Q&A afterwards. You are free, of course, to ask questions about the talk in the chat, also during the talk, and I will relay your questions to Robert during the talk if you have any. When the talk is finished, I will post the link to the Jitsi server for the voice chat Q&A in the chat here as well, and you are all welcome to switch over there and to talk to us there for a little while. I see I see Tina has already posted the Q&A voice chat server in the chat, and we will do it in the end there as another time so that you don't miss the link and get lost. So yeah, and without further ado, I will make room now for Robert and his talk about dangerous optimizations.
Howdy. Thanks, Hendrik. Okay, so let's see. Oh, Daniela's there. Yeah. She's always at my talks. And I always go to her talks. So yeah, welcome to my talk on dangerous optimizations. This is a talk I've given a few times. It's a really popular talk. People like to hear about this topic. So yeah, so I'm standardization lead at Woven by Toyota. Most of the work on internal standards for Toyota software development standards. You know, how to apply safety standards like MISRA to C++ development, and you know, what compiler options to use and how to do error handling, and also sort of software engineering standards. And as Hendrik mentioned, I chair the C committee. I participate in C++, although I've yet to write a C++ paper, so maybe I'll do that one day. And when I do, it'll probably be on integers. So we'll talk about some compiler optimizations, and a very specific one that I handled as a vulnerability note at CERT, I think around 2008. And this vulnerability note, for some reason, sometimes what people know me the best for. So it received some amount of notoriety at the time. So the premise of the talk is increasingly compiler writers are taking advantage of undefined behaviors in both the C and C++ programming language to improve upon optimizations. But these can really interfere with the abilities of developers to perform cause-effect analysis on their source code. That is, that you write some code and you assume that code is going to get translated into machine instructions that'll execute at runtime. And it turns out that they don't. They're silently removed. And now, of course, you no longer know what preconditions exist because that code never executed. And it's not only difficult for programmers, it's also difficult for static analysis tools. You know, frequently static analysis tools, they have one version of a tool that you know, needs to work with all different compiler implementations, and so they might not be you know, sort of understand the specific optimizations that various compilers implement. So so because of these, you know, issues, these optimizations are eliminating causality in software, increasing the probability of faults, defects, and vulnerabilities. So undefined behavior isn't a well understood concept. Undefined behavior is really kind of a class of portability problem. And in the standard, C and C++ standards, it's identified by saying, something like signed integer overflow is undefined behavior, or sometimes by just the absence of defining the behavior. That would be that's considered the kind of difference between explicit and implicit undefined behaviors. But when an implementation encounters undefined behavior, it can ignore that behavior completely with unpredictable results. In the C committee, because they're kind of old-fashioned, they'll say, the program is free to go off and play the game of life at that point, because the game of life was popular in the 1970s when the C committee was getting started. C++ people will say something like, nasal demons will fly out your nose. So, that's kids these days for you. It can also behave in a documented manner characteristic of the environment with or without issuing a diagnostic. And that's not as great as it sounds. So you have things like, say, int min remainder -1, which mathematically you would think would give you a 0 value. But on, say, an Intel processor, that will actually fault because it uses the IDIV instruction, which faults on integer overflow. And on the way to getting the remainder of 0, you wind up with an integer overflow with that instruction and default. Or the best case, usually that the compiler will terminate a translation or execution with a diagnostic. So the basic design of an optimizer for C or C++ is largely the same as optimizer for other procedural programming languages. This talk is mostly about C++, but I did forget to change C to C++ here and there. But when we get to the content, it's laser focused on C++. The fundamental principle of optimization is to replace a computation with a more efficient method that produces the same result. So some optimizations change behavior, and I very naively here classified them into the good optimizations that eliminate undefined behaviors and the bad optimizations that introduce vulnerabilities. So C and C++ have an as-if rule. That basically the languages are defined in terms of an abstract machine, and the as-if rule gives the compilers the leeway to remove code that is unused or unneeded when building a program, provided it gives the same, it produces the same results as required by the abstract machine. And normally this is very beneficial, but sometimes the compiler will remove code it thinks is not needed, even if code has been added with security in mind. And you could almost say especially if the code's been added with security in mind, because frequently, vulnerabilities are the result of undefined behavior in your code. And so programmers or security folks will try to add a test for an undefined behavior in order to detect the potential error. And it's very easy to invoke undefined behavior when testing for undefined behavior, right? If you just say, if this undefined behavior occurs, you've now invoked that undefined behavior, and your tests might be optimized away. So compilers follow one of three implementation strategies. The first is a hardware behavior. And this is where the compiler just generates the corresponding assembly instructions, and then you just let the hardware do whatever the hardware does. And this has been the near universal policy for many years. So many C and C++ programmers who've been at this for a while start to assume this is the way things work. And unfortunately, these languages are increasingly have semantics where, that that are defined above sort of the hardware level. So the behaviors might not be the same as what you would expect from the corresponding assembly code. There's the idea of a super deep debug strategy where nearly every undefined behavior is trapped. So this is useful, obviously, for debugging, but it typically would severely degrade performance, so it's seldom used for deploying applications. And examples of these are the sanitizers in Clang and GCC, for example. And finally, there's the total license model where compilers can treat any possible UB as a can't happen condition. And this, of course, permits very aggressive optimizations. So let's look at a kind of a simple optimization called constant folding. So constant folding simplifies constant expressions at compile time. So terms and constant expressions can be simple literals, such as the integer 2, variables whose values are not modified, or variables that are explicitly marked as being constant. So, for example, in this example I've already cited once, if we say int min remainder -1, on an Intel platform, if you generate the code for this, it could fault. But here it's a constant expression, right? So this can be constant folded at compile time, and the compiler will replace this expression of int min remainder -1 with just 0, right? So it won't have to generate any sort of division or remainder instruction. It just calculates that at compile time. So compilers can compile UB differently. So here we have some examples of unoptimized code where we're doing this exact remainder operation and printing out the result. And we have also an optimized version of this that's being compiled at 03 and printing out the result. And so if we compile this on x86 64 GCC with optimization at 00, it produces a 0, and at 03 it also produces 0. But if we do the same thing on x86 64 Clang, we get an entirely different result. And so here, right off the bat is a pretty good example of the different behavior you can get from undefined behavior. And this, in fact, is undefined behavior as well as division overflow. So we have a Godbolt link for that if you want to look at the code and play around with it a little bit. So the other thing that can happen is that compilers can just simply refuse to compile detected UB. And I actually kind of like this approach. So here's Microsoft Visual Studio version 19. When you go to compile this code, it will say overflow and constant division is undefined behavior and generate an error. So I actually prefer this. I prefer always compile time warnings or things you can find through static analysis that you don't have to test. This makes it much less likely that you're going to be able to deploy these kind of code like this with UB. And again, there's a link for that if you want to have a look. So the interesting thing is, compilers can produce different results on UB. And a lot of times when you write very simple tests to sort of figure out what sort of behavior you're getting, your test might be optimized away because you're not writing code that is needed to produce whatever result the program is supposed to produce. So it's usually worthwhile when you're writing these small tests to evaluate the behavior, your implementation's behavior, to look at the assembly code that's being generated and make sure that it really is generating the instructions for the behavior you're trying to test. The important thing is that whatever values your test is producing, they have to be used somehow, right? So they might be returned from main, or they might be printed out, something that requires the compiler to sort of work back from that and determine which statements need to be executed in order to produce that observable result of the program. Okay, so the kind of the big optimization I mostly want to talk about is deals with pointer arithmetic. So when an expression that has an integer type is added to or subtracted from a pointer, the result has the type of the pointer operand. And expressions like p sub n is also basically pointer arithmetic. It's translated into p plus n scaled for the type of the object p points to, and then that expression is dereferenced. So this is just sort of syntactic sugar for pointer arithmetic. So when you have an array, what you can do is you're allowed to form a pointer to any element in the array. This includes up into and including the too far pointer. So the too far pointer points to the element, past the end of the array. And so C and C++ allow you to form this pointer. And this was because early C code frequently would loop incrementing a pointer until the pointer equaled the too far pointer. And so if C didn't allow that pointer to be formed, that would break all that old code at this point. And so the decision was made to allow this pointer to be formed. So you can form all these pointers, and you can dereference each of these pointers except the too far pointer. So dereferencing this to try to read or write to this element would in fact result in undefined behavior. So you're only the compiler is only required to allow you to form that pointer, not dereference it. So if we look at some code where we've got an integral type, len, typically I would say size t, and we have a pointer type, what's the result? What's the type when we add or subtract the pointer to the length? So the type of res in this case is actually is a pointer to the type of the to the integral type. So here we'd have a pointer to integral type if that were size t or what have you. So here we've got the pointer plus minus len again, and len in this case will be 0. And let's say we have a no pointer in this case. You get some interesting behavior, and this behavior varies between C and C++. So C++ states that adding a 0 to a no pointer results in a no value. And the same with subtracting 0 from a no pointer also results in a no value. But adding a no pointer to any other value of len here that's not 0 results in undefined behavior. So in C, all of this is undefined behavior. It might be that C will eventually follow C++, but that wouldn't possibly be before C2Y because we've just published C2.3 and it's done. So it's there are no longer any technical changes. We're just kind of cleaning up some editing on that document before it gets published. And again, there's an example if you want to have a look at that. So here we've got an array of with a bound of n, and we've got an integer type j, and we're going to take the address of the array at some index I and assign the result to pointer. Then we're going to take that pointer and we're going to add it to this integer type j. So in this case, the question is, well, what does this point to exactly? The answer, of course, which is a solid answer for any computer science question, is it depends. So if I plus j, so this I here and this j, if added, if this value is, basically within the bound of the array between 0 and n, it will point to that element of the array. But if it's outside of this bound, then you have undefined behavior. And the same thing happens with subtraction. If I minus j is within the bound of the array, you'll access that particular element of the array. Otherwise, again, you'll have undefined behavior. And this is according to that diagram I showed earlier with the being able to form a pointer to any element of the array of the too far, but not being able to access elements outside that range. So a programmer who has some inkling of software security, probably, wants to avoid buffer overflows. And so they'll take the approach of, well, let me write a bounds check to make sure I don't access the array, beyond the bounds, thus invoking, undefined behavior. So we have a len, which is the length of the array, and let's assume that this is supplied by a user / attacker, right? So this is a external input to the program, and we've got a pointer to the start of the array, and here I find maybe my second error. So we have another pointer max, which points to the end of the array. So the programmer might write a test to say, if pointer plus len, boy, I made a lot of mistakes here. So this was supposed to say, this wasn't supposed to say that. This was supposed to say if pointer plus len is greater than max. So sorry about that. I tried to improve this talk last night. This talk I've been giving for years, and all I did was break it. So the problem with this is that no matter what model you assume, hardware behavior, hardware behavior, or total license model, there's a bug in this code. And the bug is that for very large values of len, pointer plus len can overflow, creating undefined behavior. And this kind of overflow here is not signed integer overflow. It's the overflow from we talked about earlier with adding a pointer to an integer and forming a pointer that's outside the bound of the beyond the too far pointer. So under the hardware behavior model, the result of adding pointer to a very large value of len could typically wrap around and result in pointing to an address that's actually lower in memory than pointer. So a experienced programmer who's internalized the hardware behavior model of undefined behavior might write a check like this, where they add an additional sub-expression which tests for pointer plus len being less than pointer, indicating that this value has actually wrapped around, right? Because otherwise, I mean, it could wrap around and be less than max, but still point outside the bounds of the object. And even if it wrapped around to the point where it was pointing into the array again, I really wouldn't trust it at that point, because that's just coincidence, really. At that point, that's not planned. So this, is intended to complete the test and make sure that we haven't supplied a very large value of len that results in wraparound. So now we have a complete test for wraparound. Now the problem with this code is the C and C++ standards assume that an overflowed pointer is undefined, which allows implementations to assume pointer overflow never occurs on any architecture. So assuming the total license model in this case, we have pointer plus len less than pointer. When is this expression true exactly? It's only true when pointer plus len would overflow, and this is clearly undefined behavior, and it's also undefined behavior that's quite detectable by the compiler, right? They can just look at this expression and tell that for this expression to be true, undefined behavior had to have occurred. So there are a lot of cases we would like our compiler to detect that we're accessing storage outside of an array, and it can't, but this is a case where it most certainly can detect this. So if we have overflow and we're using the total license model, the compiler can assume that the UB never happens, right? And that means that this code, this test is unnecessary and can be removed. So this code again now is considered dead code, and the compiler will eliminate the dead code following the as if rule that we discussed earlier. So we're back to this, and we've already talked about why this test is insufficient. So we basically, the compilers basically eliminated this, at least part of this bounds check that we introduced to avoid buffer overflows. So that's not great. Now, another way to look at this optimization is that really the optimization being performed here is an algebraic simplification. So optimizations can be performed for comparisons between P and V1 and P and V2, where P is the same pointer and V1 and V2 are integer variables. So total license model allows us to be reduced to a comparison between V1 and V2, between the two integer values. However, if V1 or V2 have values that will overflow when summed with P, the comparison of V1 and V2 doesn't yield the same results as actually performing the addition and then comparing the sums. So an interesting sort of generalization of this is that computer arithmetic doesn't always obey the algebraic identities of mathematics because, integers on digital systems are sort of a model for real world integers. They're not really the same, and so models are sometimes useful, but they're always wrong, right? If they weren't wrong, sometimes they wouldn't be models; they would be the actual thing. So when we look at our example and we want to examine what happens to this expression, you'll see that this expression is equivalent to this second expression. We can just add 0 to the right-hand side of the inequality. That doesn't change, the algebra. And once you're here, right, you can see now that you've got the pattern of P plus V1 compared to the same pointer P plus the second value V2, right? So our optimization tells us that we can reduce this to a comparison between V1 and V2, which gives us len less than 0. And we know this is impossible because len is unsigned value, so it can never be less than 0. And so from this perspective, it seems very natural that this test can be eliminated, right? It's an impossible condition. So sometimes I forget why I put this in, but if you look at the difference between O0 here on the left and O3 here on the right, you'll see that we have at least one additional jump. So this is, this is the code with both test, and this is the optimized code with the first test removed by the compiler, optimized away by the compiler. So if you're aware of this problem, it is actually pretty easy to fix. So, for example, if you get some sort of diagnostic, but it's not that easy to get a diagnostic for this. So, for example, if pointer is less than or equal to max, which in our sample program it is guaranteed to be less than or equal to max, you could just change the test to be len greater than max minus pointer, right? So in this case, because max is greater than pointer, that guarantees that this expression won't wrap around, and consequently, there's no sort of obvious undefined behavior that the compiler is going to optimize away. So this expression will be retained by the compiler and will result in the appropriate instructions being generated to fully implement our bounds test. So these were originally problems reported in an early version of GCC. And the people who had these problems were actually the Plan 9 developers at Bell Labs. So it's a pretty good example of, experienced programmers who, are quite expert. And that's really the type of programmer that's likely to make this mistake, right? Because they've been programming a while. They've internalized this hardware behavior model where pointers will wrap around. So in GCC, so this optimization went into a much earlier version of GCC. I think it was GCC 4, but in GCC 8, some changes were made where signed integer overflow is now considered undefined by default at all optimization levels, unless some flag is used to change that behavior. So when we originally, when the CERT CC reported on this problem back in 2008, the response from the GCC development community was to introduce this no strict overflow and a warning warn on strict overflow. And as of GCC 8, these features have sort of been deprecated. So no strict overflow now, just maps to FRAP V and FRAP V pointer. So this no longer does anything special. And therefore, I probably would not use this anymore, because it's, if anything, it's maybe a little misleading, right? I would just use the flags that are actually being used now. So FRAP V instructed GCC to assume that signed arithmetic overflow of addition, subtraction, and multiplication will wrap around. So this flag will disable optimizations that assume integer overflow behavior is undefined behavior. And so this was the option enabled by default for the Java front end back when GCC had a Java front end. Because Java, Java is a very different language than C or C++. Java has an emphasis on portability over, say, performance. And so Java defines integer overflow, signed integer overflow as having modulo behavior. And so this is the sort of behavior that you would get with the FRAP V flag. There's also the FRAP V pointer that instructs the compiler to assume that pointer arithmetic overflow on addition and subtraction wraps around using 2's complement representation. So this would disable optimizations which assume pointer overflow is invalid, such as the optimization we just examined in some detail. Right, this would prevent that optimization from being performed, and that would preserve your bounds check. And here we've got just some Intel instructions that demonstrate the behavior with FRAP V. And you can see again that we have both jumps being preserved. So there was this warning on strict overflow that you could set to different levels, 1, 2, 3. 3 would detect the problem we identified with the bounds check being eliminated. But that flag has been deprecated as of GCC 8, and so you can't really use it anymore. The documentation, the GCC documentation doesn't really tell you it's been deprecated. You have to find that information in the release notes for the 8.0 version. But in deprecating it, they didn't, first of all, they didn't tell anyone they deprecated it unless you saw those release notes. It's still in the documentation, but doesn't say it's deprecated in the documentation. And by deprecating it, what they mean is that they're no longer fixing problems with it. So it's still there, and it still appears to work, but it's starting to deteriorate. So it's got sort of problems with false positives, and GCC won't do anything with it. And so basically that flag has become untenable. And so what GCC, as of GCC 8, what they recommend is it use the sanitized flag for signed integer overflow. So signed integer overflow, where the result of a signed integer computation can't be represented in the type. This would include all the checks covered by FTRAP V, as well as checks for signed division overflow. And we've talked about this one, int min remainder minus 1, or int min divided by minus 1, which overflows on 2's complement architectures, or int min remainder minus 1, which also overflows. But it won't check for lossy implicit conversions performed before the computation. So this is now recommended, and this is a good idea to sanitize your code, but this, of course, is dynamic analysis, and the only way this is going to find your problem is if you exercise the code path that overflows. And so you can use dynamic analysis, and you should, but you have to thoroughly test it, with your full suite of tests. And also you need to, you can do other things like try to use fuzz testing to, exercise all the paths in your code. Okay, so recommendations, and I think we're ending with pretty good time, so we'll have time for some questions afterwards. So I guess this is pretty obvious. You want to avoid undefined behaviors in your code, even if your code appears to be working. Undefined behavior is, again, it's actually a portability issue, right? So you can have undefined behavior in your code and have your executable actually be correct. But the problem is that undefined behavior can be changed at any time. So your compiler vendor, GCC or Clang, whoever they might be working on an optimization that takes advantage of that undefined behavior, and you might upgrade to just a maintenance release, and they might select that time to deploy this new optimization, and suddenly the behavior of your code changes. This is really true. There's a lot of code that's been working for decades that does things like assume, I can have a couple objects in memory and increment a pointer to point to the next object, and because that address, because that second object is at that address, they'll assume a hardware model and say I can access that new object. It turns out that's not really true anymore, and people get upset. Really, not because C and C++ or high level assembly code. It's because these languages now have semantics that are being enforced by the compilers. So it's a good idea to find and eliminate any dead code you might have instead of letting the compiler do it for you. For the most part, people don't write code with the expectation that it won't be executed. There are some cases where this might be true. So you might have, for example, a switch, and you might, switch on an enum, and you might have a default case that should never execute, right? So your expectation there would be that code would be optimized away, but it's good software engineering practice to leave it there in case a new enum constant is added. There's a new value, and so that you'll be able to detect a change in your code and a potential defect. So some optimizations can eliminate undefined behaviors, while others can introduce vulnerabilities. So basically it's kind of a wash when you optimize your code. Overall, I would say that optimizations tend to eliminate more problems than they introduce. And they also make your code faster. So the point of this talk, I think because I have a reputation as a security person, you probably get to this point in the talk and expect me to tell you to disable optimizations, but I don't really agree with that. So I think you should go ahead and compile at higher optimization levels, generally speaking O2, but you might also use O3 for hotspots in your code. So the strict overflow flag I was talking about, where you can set this equal to 1, 2, 3, 4, 5, is really busted in GCC. So I would not recommend using this anymore. It's also available in Clang, but in Clang it never did anything. It's just there. So if you copied your flags over from GCC, your code would build, but the flag has always been ignored, so it doesn't do anything there either. So this is bust it, and best to just not use that anymore. So this sanitized signed integer overflow is the preferred way to audit code, but it's dynamic analysis. So to be effective, you have to make sure that you instrument your code and then exercise it. So that's all I have. Here's my contact information. You have my email address, which is usually the best way to get a hold of me. And, I'd love to talk about this kind of stuff. So feel free to email me and chat me up on UB or C or C++ or whatever coding topics you'd like to chat about. So, yep, over to you, Hendrik.
Yeah, thank you for the interesting talk, Robert. Now, before we head over to the voice chat server, there's one question from the chat I want to relay to you in the end. And it's this question. So you talked a lot about C arrays, and someone asked what happens if we exchange all the C arrays for std array from C++, or are there also UB problems with std array from C++?
Yeah, there can be undefined behaviors with std array, but they're entirely different problems. So using not using C arrays in C++ is not a bad idea, just to avoid them completely and use std array. There's still things you have to be concerned about, but it's a different set of problems.
Yeah. Thanks for answering the question. So as mentioned in the introduction, we can now head over to the voice chat if you all are interested. I will post the link again in the YouTube chat, so it should be there now. So everyone who is interested to talk with us or talk for a little while with Robert or to exchange about the talk with each other, feel free to hop on over there and we will see you there. And yeah, thanks for the talk and thanks for listening to us, everybody.
Okay, see you there.
See you.